In this video, I'm going to keep it very much short and straight and to the point, but what we're going to be doing is we're going to be exploring counting principles, explicitly the fundamental counting principle. So by the time you leave this video, you should be able to tell somebody else what the heck this fundamental counting principle is and why we use it. Okay, so let's go ahead and start by considering some thought experiments here and talk about what we mean by counting the possible outcomes for an experiment. But let's go ahead and take a look at this. It says 8 pieces of paper numbered 1 through 8 are placed into a box, and it says the first number is drawn from the box and its value is recorded. It is then replaced, and then a second number is drawn from the box and its value is recorded. So one really important thing to note here is this: it was replaced. Okay. Also this, my question is, how many different ways can a sum of 12 be obtained from these two values? When we say sum of 12, we really mean how many ways could they add up to be 12. So what we're going to do is this: we're going to list this. We're going to say number 1. So we got number 1 and number 2, and we're drawing these things out of the box, and what I want to do is I just want to illustrate this here. So how many different things could I choose out for number 1? Well, it could be a 1, a slip of paper with a 2, a 3, a 4, a 5, a 6, a 7, or an 8. Okay. Now we did say this. We said once we draw a value here, what we're going to do is we're actually going to put it back and we're going to draw another slip of paper. So what this means is when I draw the second number, I actually have all of the original numbers available to me to draw out. So we say, well, what combinations would add up to be, say, 12? So I suppose I could get a 4 on the first one and an 8 on the second one. So we say it could be a 4 and an 8. So I'm going to list this out here: a 4 and an 8. Or we could say an 8 and a 4. You have to understand that these are different possibilities. To get an 8 on the first number and a 4 on the second number is different from a 4 than an 8. We say, oh, what else? How about a 5 and then a 7, or a 7 and then a 5? So we say I grabbed a 5 and then I grabbed a 7 on the second one, or I grabbed a 7 on the first one, put it back, and then grabbed a 5. And then last but not least, we say you could get 6 and then get a 6. Okay, so your first number could have been a 6, and then you put the 6 back and you grab the 6 again. But these are all of the possible ways that we could necessarily get a sum of two numbers that comes out to be 6. So we say 5 outcomes in this experiment would provide us with a sum of 12. Now, reading through this again, what I'm going to tell you is it says 8 pieces of paper numbered 1 through 8 are placed in a box, just as in example 1. But it says this time, though, after you draw the first paper out and record its value, it is not replaced. Okay, so it's not replaced and put into the box. It says how many different ways exist now for the sum of 12 to be obtained from these two values. Well, what I hope you see is this. Let's say you took, say, the 4 out on the first one. I say, oh, well, the 4 is gone. Then, I would not, sorry, the 4 would be gone, and I wouldn't have 4 to choose from in the next one, so I could choose any of these other things. So I suppose I still could choose an 8. So 4 and an 8 and an 8 and a 4 would still work here. But the moment that you drew this 6 and the 6, the idea is that once you took the 6 out on the first one, could you draw a 6 on the next one to add up with the original 6 to come out to be a sum of 12? And you couldn't. So what I'm going to indicate here is this. We say that this down here, we could still do a 4 on the first one, then an 8. Or we could keep and take the 8 out, keep it, and still draw the 4. Or we say we could draw a 5 and then a 7, or a 7 and then a 5. But the idea here is that this 6 and then a 6 could not happen. Okay. So one important thing we want to do when we pay attention to counting situations is whether or not we're replacing things between the events. So here's the basic gist of what I want to do before we kind of move into the fundamental counting principle, but is ask the question, would there have been a quicker way that I could have counted these things up without having to list all of the possible outcomes and start counting from those? Could I count a little bit more quickly? And actually the answer to this is yes, using the fundamental counting principle. Now, right next to this, we're also going to give this another name. We refer to this as the multiplication rule. And the reason why we call this the multiplication rule is essentially because we're going to use multiplication to determine the number of possible outcomes. So let's read through this. It says, considering the last example, it was very easy to write out the possible outcomes that gave us sums of 12. So we could actually write those things out, but I say in many experiments, we need to rely upon formulas to aid us in counting the number of possible outcomes for given events. And the reason why is because in a lot of experiments, you have a lot more than, say, 5 or 4 possible outcomes, more than you could write out yourself. So we say the most important of our counting formulas is referred to as the FCP, or the fundamental counting principle. So let's be really clear on this. We say let E1 and E2 be 2 events. Okay, so maybe those 2 events, we'll write them here. We say E1 and E2 are 2 events, and let's say this first event is choose a number, and the second event is say, choose another number. We say the first event, E1, can occur in M1 different ways. So what I'm going to fill out here is essentially this. Under this spot here, we say M1 ways for this thing to happen, okay? And we say that event 2, there are M2 ways in which that number could be chosen, say. But if you wanted to find the number of ways that two events can occur in sequence, what we'll say is this. We could just take the number of ways the first thing happens times the number of ways the second thing happens. And honestly, you could see how this could be extended to more than one or more than two events. If we had a third event, we had an M3, we could say the number of total ways this happens is M1 times M2 times M3, where each of these numbers represents the number of ways that thing can happen. So we're just going to piece this together really quickly. We use our FCP all the time. But look at these three examples down here. It says how many different pairs of the English alphabet are possible. So they're really saying, well, how many different first letter, second letter combinations can we use? The first thing I want to do is this. Just like I did right here, I'm going to represent my events by underlying blanks. And I'm going to put, a multiplication sign right between them. So we say event 1 here is this. And actually, I'm going to label these out. We say event 1 is letter 1, essentially. We're going to choose one letter, and we say event 2 is letter 2. And what I really want to know is this. Well, how many different letters could I choose from in this first spot? How many ways could I choose a letter here? And we say, well, 26. There are 26 letters in the alphabet. And you know what? How many letters could I choose from to put in the second spot? I'm going to say 26, and the reason why is because I didn't say that once you chose a letter, you couldn't reuse that letter. So in this case, we get 26 times 26, or 26 squared, and this would be easy to go find on a calculator here. We say 26 times 26, and we get 676. So there are 676 total pairs that we could write in this alphabet pair combo. Okay, so let's look at this. We say a combo lock will open with the right choice of three numbers, and we say from 1 to 30, okay, inclusive. And when we say inclusive, it means it includes 1 and 30. But we say how many different combo locks are possible. When we say that it has to have three numbers, the first thing I'm racing to do is this. I say number 1, number 2, and number 3. And I'm saying, well, first of all, how many digits do I have to choose from for this first number? Well, according to this, it says 1 through 30. So we have got 30 ways to choose this number. And then could I use the same number again? Well, on a combo lock, I suppose I could, use the same number again. There's no rule against it. So I could say 30, and then I could use 30. So the idea here is this. We're going to get 3 cubed times 10 cubed. In other words, you get 27 with 3 zeros after it. So there are 27 different combinations that we could use here. And then one last time we use this fundamental counting principle. It says telephone numbers currently have 10 digits. How many different telephone numbers can you make me within each area code? Okay, so here's the kicker. We say, note that the telephone number can't start with a 0 or 1, and it's in each area code. So if we're saying that a number is this, it's an area code, we say area code, and then we have the prefix, and then the suffix of the number, like this here. Then we would say, well, this right here, we say within each area code. If it's a given area code like Omaha, we say 402. What I'm basically saying is this. If it's got to be 402, then you only have one number that you can put here. It's got to be a 4. And only one to put here, it's got to be a 0. And only one to put here, it's got to be a 2. So all of these right here, they don't really count because we're saying within this one area code, how many different numbers can you make me? So now let's consider this. A telephone number, it has to consist of 10 digits, and here are 10 digits here. And we're just going to fill in how many digits I have to choose from in each spot. So 0 through 9, that's 10 digits for each spot because you have to include the 0, but we say it can't start with a 0 or 1. So if I said, well, how many digits do we have to choose from to go right here? Well, usually there are 10, but I can't use a 0 or 1, so there are only 8 to choose from there. Okay? And then all the rest of these, I suppose I could use the same digit again and again and again and again. So what we end up with here is this. We get 8 times 10 to the, we have 6 tens here. In other words, we get 8 with 1, 2, 3, 4, 5, 6 zeros on it. So there are 8 million different phone numbers you could make me in this scheme within a given area code. So that's how we use the fundamental counting principle, and we'll kind of build on that in the next video. Cheers.